We have a little Newton comment. Just remember, most energy comes from the sun. The plants convert that energy into chemical energy, and you could go ahead and read through the rest of it. So heat moves in one direction, from negative Q to positive Q. What this means is it moves from hot to cold. So why is there that negative Q in that situation? So in thermochemistry, we use a negative to represent something a little bit different than maybe you're used to seeing negatives. So you'll see 5, 0, -5, and you think, okay, that's not a real number. You can't have a negative something. So in thermochemistry, we use positive and negatives to represent direction. So if something is hot, it means it has energy that can go out or that is released. And we use a negative sign to represent that that's happening. And then our positive sign is energy in or energy absorbed. So if I had negative 200 kilojoules of energy, that means that I'm going to be able to pass 200 kilojoules of energy to something else. And if I have a positive 200 kilojoules, what that means is that I need 200 kilojoules to go ahead and do whatever it is that I want to do, or I'm required to have that much energy. So those positive and negative signs do mean something. So we have 2 examples to make sure we're understanding this. So if our ice is in room temperature water, so room temperature water, comparatively, the one that's hot compared to the ice is going to be the room temperature water. So the water is going to be hot. Of course, that's comparatively to the ice, which is cold. So the hot is the one that's negative Q, and the cold is the one that's positive Q. How does heat flow? From hot to cold. It's flowing into the ice, and of course this is surrounded in. And this makes sense because, you've seen ice. When you leave it outside and the sun hits that ice and it keeps hitting and hitting and hitting that ice is going to start to melt. The ice is absorbing, positive Q, the heat from its surroundings. Now, in contrast, we have a hot metal in room temperature water. Think of like a blacksmith or something, tools that he just made. So now we have hot metal and we have room temperature water. So relatively now the water is cold compared to the metal. So the metal is the negative Q and the cold is the positive Q. And remember, it flows from hot to cold. And it's going to keep doing that in both cases until they get to the same temperature, until each system reaches the same temperature. And we call this thermal equilibrium. So hopefully that visual really helps. Now, this is a great phrase that you might have heard growing up as a kid. Shut the door, you're letting all the cold air out. But we just talked about this. You don't shut the door letting all the cold air out. It's hot. Hot is what does the moving. You're letting all the hot air in, because that hot air is what has the energy and is coming in and heating the cold air. And this is just another little illustration. And this one also has these little lines, and this represents that these little balls or atoms are moving, because everything is moving. But the things that are hotter, and it's not a really great contrast, but the things that are hotter, the red ones, have more of these. So the red side has higher, they call it kinetic energy, that's the movement of the molecules, than the lower temp. So they haven't touched each other yet, but as soon as they come into contact, again, the heat, the high energy molecules are transferring energy, kinetic energy, to the colder molecules. And you'll see the colors kind of begin to average until you end up at thermal equilibrium. We're never saying that the molecules stop moving, but we are saying that when it's hot, they are moving faster than when it's cold. So with all of that information, see what you can come up with for this section. Go ahead and pause it.